Hi, everybody. Thanks for joining today's session of the Chandra Data Science Workshop. We have quite a large group of people speaking today, a lot of lightning talks in what I'm calling the thunderstorm session of this meeting. I'm very excited for everybody to have the opportunity to share their work that they're going to present to us today. So I'd like to start and introduce the session. So our first speaker today is Yue Hu, who's going to talk to us about the novel insight of probing magnetic field morphology in galaxy clusters. And Yue Hu is coming to us from the University of Wisconsin-Madison. You can start sharing your slides, Yue Hu.
Can you see it?
Yep. Can you? Yep. Looks good.
Okay. And hello, everyone. I'm Yue Hu, and from the University of Wisconsin-Madison. And here I'd like to present a new method of tracing magnetic field in galaxy clusters, which uses only X-ray emissions in observations. And this new method actually based on the turbulence properties in intercluster medium. And as we know, the turbulence in large scale ICM is hydrodynamics dominated because the magnetic field is weak. However, at small scale ICM, the turbulence becomes MHD turbulence dominated because the magnetic field's back reaction becomes more important. And the large scale hydroturbulence has important properties because the magnetic field in the intercluster medium is very weak. Therefore, the magnetic field lines preferentially follow the turbulent flow. And in this case, if we calculate the intensity gradient of the turbulent flow, we can find the intensity gradient actually is perpendicular to the magnetic field. And this is a similar, and here is a similar situation for the small-scale MHD turbulence. Because for small-scale MHD turbulence, the turbulent eddy is anisotropic, which means the turbulent eddy is elongating along the magnetic field lines. And in this situation, we still have the intensity gradient perpendicular to the magnetic field direction. Therefore, we can, for both the case of large-scale hydroturbulence and small-scale MHD turbulence, we just needed to know the direction of the intensity gradient and rotate it by 90 degrees. We can get the direction of the magnetic field. And here I show an example of the magnetic field traced by the intensity gradient technique. And here is the Perseus galaxy clusters observed by the X-ray emissions. And here we can see that the magnetic field lines predicted by the intensity gradient is following the slanting arm. And this actually agrees with the numerical simulation in Zhu Hu et al. 2011. And also, we are trying to quantify the magnetic field directions in Perseus cluster. And then we introduce a parameter, the alignment measure AM. When we have AM equals to 1, we have the magnetic field parallel to the radial direction with respect to the galaxy center. And if we have AM equals to -1, the magnetic field is perpendicular to the radial direction. And what do we find is for the Perseus cluster, at small scales, the magnetic field is preferentially perpendicular to the radial direction. And this orientation changes at large scales. Because at large scales, we find that the magnetic field is preferentially follow the radial direction. And also, we expand our analysis to several clusters. And we find this tangential magnetic field direction with respect to the galaxy center only can be observed at Cooper clusters. For example, the M87 and the 87. But in the non-Cooper clusters like Coma clusters, there is no such preferential magnetic direction because we find that AM is close to 0, which means the magnetic direction is more close to be random.
1 minute.
And here, yeah, that's all my talk. Thank you.
Thank you very much, Yu. We have time for one question. If anyone has a question, please put it in the Slack channel, or if you have to use the Q&A, use the Q&A. I just want to remark that those are really spectacular images in this the study that you're doing. Sounds really interesting and impactful.
Thank you.
Okay, if we don't have any questions now for Yue Hu, I do encourage you to add them to the Slack channel later. We can take questions for Yue Hu whenever he's available to answer them. Thank you, everybody. Let's go on now to our next speaker. Our next speaker is Bharti Arora, who's going to talk to us about W12A new results from a long-term X-ray observations. And Bharti is coming to us from the Aryabhatta Research Institute of Observational Sciences. Go ahead.
Thank you. Yeah, thank you so much. Hello, everyone. My name is Bharti, and today I'm going to present the results we have obtained for a Wolf-Rayet star WR121A. So WR121A, it's a WR star which is located towards the galactic center. These are the equatorial coordinates of this source, and many times speculations were made previously that this object belongs to a binary system. And the most probable components of this binary are a WN7 type of a Wolf-Rayet star and in a binary orbit with an OB type star. This object was first detected in X-ray by ASCA Galactic Plane Survey in 0.7 to 10 keV energy range. Therefore, we wanted to see the motivation to study this source is to systematically search for its binarity. And for that, we have used archival X-ray data from XMM Newton and Chandra as listed in this table. So this source was observed for a total of 10 epochs. By using XMM Newton and Chandra, and out of 10 epochs, mostly Chandra has observed this source for most of the times. So here I have shown the Chandra X-ray light curve of WR121A in 3 different energy bands: 0.5 to 8 keV, 0.5 to 2 keV, and 2 to 8 keV. So in the 0.5 to 8 keV energy range, you can see that in this light curve, you can see that there is some kind of variability is seen in this light curve. So to check if there is any periodicity in this data, we have performed this periodogram analysis, and a period of 4.1 days has been seen to be associated with this light curve. So from where this period might be originating, to see that, we have performed its X-ray spectral analysis. So we have fitted the XMM Newton and the Chandra spectrum of WR121A using 2 temperature thermal plasma emission models. This is the form of the model which we have used. This takes care of the ISM as well as local hydrogen column density present around the medium. And in the left figure, I have shown here the XMM spectrum of WR121A fitted with the 2 temperature plasma model. After fitting this spectrum with the 2 temperature components, we have estimated the flux in 3 different energy bands: broad, soft, and hard. Broad is from 0.3 to 10, and soft and hard we have demarcated from 0.3 to 2 and 2 to 10 keV. And in these 3 energy bands, flux is from this source has been seen to be varying with the orbital phase, as shown in the right side of this figure. So here orbital phase means that the orbital phase defines the relative position of the 2 stars in a binary of period 4.1 days. So here you can clearly see that the flux in all 3 energy bands is varying with the orbital phase. So this flux is maximum close to 0.4 phase and being minimum around phase 0. So these flux variations suggest that these might be coming because of the wind collision in this massive binary system. This happens when the 2 stars in a massive binary, they are bound together by gravity, and when both have their own winds. And when these winds collide with each other, they give rise to the formation of hydrodynamic shocks in the wind interaction region. And because of that, the temperature in the post-shock region increases, and it reaches till 10 raised per 6 to 10 raised per 7 Kelvin, which give rise to the X-ray emission from the wind interaction region.
1 minute.
And these kind of flux variations, okay. And these kind of flux variations are very typical to the colliding wind binary systems. And when we try to see that what would be the probable orbit of the system, it was found to be almost circular among the category of other WR plus O binaries as given by this plot. So so to conclude this talk, we could say that WR121 is a colliding wind binary with an orbital period of 4.1 days, and the flux variations could be coming because of the occultation of the wind interacting region by the component stars in a circular orbit. So that's it. Thank you so much.
Thank you so much, Bharti, for that excellent talk. Very informative. We don't have time for questions right now, but I do encourage you to put questions in the Slack for Bharti if you have any. Erwan, I haven't seen your slides, haven't been able to get access to them yet. I'm going to bump you now, and we're going to go on to Erwan, Quintin in our schedule until Eran and I figure out how to share their slides. Erwan, can you take this position?
Yeah, sure. Let me just share my screen. Here we go. All right. So, hi everyone. I'm Erwan Quintin. I'm a first-year PhD student at Toulouse, France, under the supervision of Nathalie Webb, and I'm going to present you my work on a multi-wavelength study of the transient sky. So, the history of transient astronomy begins, at least for the Western transient astronomy, in 1572 with Tycho Brahe, a Danish astronomer who was observing a well-known constellation, Cassiopeia, and he noticed a new star. He studied it over the course of a year, saw its dimming, and wrote a book about it, De Nova Stella, which coined the term for novae and supernovae. And on the right, you can see the picture, composite picture of what we can see today, which is a supernova remnant. So this is the first example of transient astronomy. And in fact, a lot of objects in astrophysics are variable, and some of the most interesting ones are. So in this little graph, you can see some of the variable objects we can see in the sky with their typical timescales on the x-axis and the variability amplitude on the y-axis. So on the left of that dotted line, you can see what we call short-term variability, which means that those objects are variable within one single Chandra or XMM Newton observation. So we have stars with stellar flares and X-ray binaries. This was covered yesterday in a very good talk. But there is also long-term variability, so with typical timescales over a day, and those require at least 2 observations to detect variability. So we have gamma ray burst afterglows, supernovae, and I'm particularly interested in the 3 types of objects on the right. So those are tidal disruption events, when a star gets disrupted by the tidal forces around the black hole. Those are extremely rare, and we only know a handful of them in X-rays. We also have ULXs, ultraluminous X-ray sources. So those are exotic X-ray binaries that are extremely luminous, and their luminosity is not very well understood to this date. And finally, we have, of course, AGNs. Everyone knows what AGNs are, but some of them are change in look AGNs. So this means that they are variable. And this is generally explained by a change in absorption, which is due to a cloud of dust coming in the line of sight. What's interesting about those 3 types of objects is that they are extremely rare. So tidal disruption events, we know only a handful of them in X-rays. ULXs, we know a lot of them, but what's interesting is that some of them have pulsations, and we only know 7 pulsating ULXs, or 8, as we'll see later. And changing look AGNs are also quite rare. They show observational diversity. So all of them have different observational properties. So for instance, so there is a lot of observational diversity. And overall, those 3 types of objects have new or poorly understood physics. So it's extremely interesting to find new ones and new examples of those objects. So this is one of the reasons why we are witnessing today the dawn of time domain astronomy, which is focusing on detecting events that are time dependent. So we have, of course, the Vera-Rubin Observatory, which is in optical and which will have a return time of 3 days. So this is excellent to find transient events. We have neutrinos, gravitational waves, and in a lesser extent, Rho-zeta will allow to have a certain level of consistency and of long-term follow-up of X-ray data, since it will provide us with, I think, five full sky coverage of X-ray data. So overall, time domain astronomy is multi-messenger and multi-wavelength. Meanwhile, I'm going to shortly explain you how XMM Newton handles transient events. So let's say we have a typical light curve of a transient X-ray event with a serendipitous detection of the event at the peak. XMM Newton has a 1-year proprietary period during which the data is only available for the PI of the observations, which means that nobody has access to it. And if the PI is focused on the target of the observation and doesn't notice the transient object because it's on the edge of the CCD or whatever, then we have to wait a year for the data to be published, for someone to find it, to ask for a follow-up, get the follow-up. And finally, when the second observation is done, it's nearly 2 years later, so the transient is generally over. So one can wonder, what if we tried to detect X-ray transient in a more automatic fashion using 20 years of existing data? So let's go in more details about how to search for variability. Once again, the typical light curve of an X-ray variable object. In the case where we're extremely lucky, we get 3 data points, 1 at the peak, 2 in the quiescent state. Then we can conclude that there has been variability. There are different ways to quantify variability and to take into account the error bars. And the way we chose to work was to take the most pessimistic assumption of variability. So that means that we take the max flux and the minimum flux, and we either add or subtract the error bars. This means that the variability can sometimes be lower than 1 in the case of a constant source. So to detect long-term variability in this way, we need to have a lot of points and be lucky. There already exist some projects to find variability in this way. So for instance, the Extras project, which has done an outstanding job at studying short-term variability and periodicity in a systematic way for XMM data. And they also worked on long-term variability for 3XMN DR4 sources. So this is an older version of the catalog. But our method is quite different since we work on cross-correlations. So what the image is pretty simple. Let's say there is an XMM Newton observation of the sky, and XMM Newton detects a source here. 6 months, 2 years later, Chandra observes nearly the same patch of the sky and detects a very bright source. If Chandra and XMM Newton don't talk together, they won't know that something happened here. So what we do is we correlate those sources and identify the physical source that is behind it. And in fact, we associate the XMM Newton and the Chandra source. What this gives us is this type of light curve with a long-term variability that is only available because we identified the fact that it was, in fact, the same source. So this method increases noticeably the number of detections per source that we get. To be more precise, we used 5 different X-ray catalogs. So the first 3 ones are the first 3 major X-ray instruments. So XMM Newton, Chandra, and Swift, which all have their ups and downs. And more interestingly, we also used 2 XMM Newton additional catalogs. So the first one is the SLU catalog. So what it means is that between 2 pointings, XMM Newton lets its camera opened, and it covers a large patch of the sky, but with very low sensitivity. So if there is a very bright event that takes place, we'll most likely catch it. So this has a huge coverage, nearly all sky, but a very low sensitivity, roughly similar to Rosat. And we also use the stack catalog, which is basically the XM Newton normal catalog, but which was built on stacked observations. So it allows to detect new faint sources and also to retrieve detections of sources that were missed in, let's say, 1 or 2 observations. So all those catalogs complete each other. And the precise method we used was we computed the pairing, so the 2x2 correlations of those catalogs, taking into account the positional error and the astrometry error between the catalogs. Then we merged those pairings into what we call a master source, which should correspond to a single astrophysical source. We encountered some problems because of the different spatial resolution properties of those telescopes. So the way we chose to do this is in a very conservative manner. We excluded any conflictual or ambiguous association. And finally, the position and position errors of the sources are the weighted average. But what's interesting is that this method also allows us not only to focus on detections, but also retrieve information on non-detection. Let's take the same example. Chandra detected a very bright source. 2 years later, XM Newton saw absolutely nothing. In the Chandra catalog, we have 1 detection. In the XM catalog, we have nothing at this place. But this is not, this gives in fact a lot of information, because if a source is not detected, then it means that it's below the sensitivity level of the telescope at this space and time. This depends on a lot of observational parameters. If we reverse this thinking, this means that by computing the sensitivity level, we get an upper limit on the source's flux. And this is what we have done. We have taken into account all the Chandra Swift sources that are in XM Newton's field of view, but were never detected by XM Newton. And for those, we retrieved upper limits. So this was done using Rapid XMM, which is a server that computes XM Newton in a very fast manner. And this gives this type of light curve. So we get 1 detection and some upper limits that are sometimes enough to conclude about the variability of the source. Finally, to improve our knowledge of multi-wavelength variability, we took into account OM, which is an optical and UV telescope on the side of XM Newton. And this provides simultaneous multi-wavelength data points, which is basically the holy grail of transient study, because it's extremely important to identify an object to have a lot of different wavelengths at the same time. So there are many sources in OM, but only a few of them match with X-ray sources. And the systematic correlation is, to this date, very underexploited. So I'm going to show you some results of our method. Some numbers at first. So we have over 1 million sources, and about 10% of them are built with correlations between at least 2 catalogs. We also computed over 300,000 upper limits on XMM undetected sources. So most of those are Chandra sources that are just too faint for XMM to detect. But sometimes there are also variable sources, a lot of GRBs from Swift that were not detected in XMM Newton, this kind of variable objects. In the end, it gives nearly 3 million data points. So this plot here basically sums up the point of our method. This shows the distribution of variability of the sources before and after we correlated the catalogs. In blue, before the correlation, so this is by taking the catalog at face value. And in orange, this is after the correlation. So what you can see is that the distribution is slightly shifted to the right. This means that we have indeed improved the overall variability of our sources, especially in the extremely variable regime here. So this shows that this method works. But then we need to dig into those 3 million data points, and we need to find selection criteria to find interesting sources. There are a lot of them, long or short-term X-ray variability, of course. We can also use the optical variability. We can work on the spatial position of the source, whether it's at the center of the galaxy or at the periphery of a galaxy. This would mean that it's a ULX, for instance. We can add selection criteria on the spectral shape. So for instance, softness could be a hint that there's a TDE. And the takeaway of this is that most of the interesting sources are yet to be found and still lie in the archival data. I'm going to show you a quick example of one source that we found using this method. So this is NGC 7793 ULX4. So this data point is what lies in the XM Newton catalog. Well, here only one point. When we computed the upper limits, we get that the source was in fact observed 13 times, but detected only once. And this tells you that something happened. And finally, when we take into account Swift, we get this. There was clearly a transient event here that took place. Interestingly, Chandra also observed this patch of the sky about 6 months earlier without detecting anything. So NGC 7793 is famous for those of us that know ULXs because it's a galaxy, it's a nearby galaxy that already is known for harboring at least 2 variable ULXs, one of which is P13, which is one of the 7 known pulsating ULXs. So this pulsating ULX is the reason why this galaxy was so much observed. So on the left, the optical, yeah, thank you. And on the right, the XM Newton observation with here ULX4 and Chandra 6 months earlier without anything at this place. So we looked for pulsation. Like I told you, pulsation are quite rare, and we found one. So this turns out to be a good candidate pulsating ULX, which would mean that this galaxy is the first galaxy to host several pulsating ULXs. So our catalog allows to dig into 20 years of archival data, but it also allows to detect newly observed transients by simply taking the new detections and comparing it to master sources and see if this adds variability. So we took 2 random months of XM Newton data and tried to see if we could get transient alerts. So with a fixed variability threshold of 3, we get about 1 alert a day. And this is the nature of the objects we found. A lot of stellar flares, which was expected. A lot of variable agents, we were expecting them, but not so much. Some objects were not identifiable because of the poor X-ray positioning. And interestingly, we had 2 GRBs and 1 quasi-periodic eruption. So this figure shows the kind of variable AGN we get. So on the top row, we have the X-ray light curve, multi-instrument, and the X-ray spectra. And on the bottom row, we have the multi-band optical data, light curve, and spectra. What this shows is that the optical data and the optical variability is correlated with the X-ray variability. So this confirms that something interesting is happening. And this change in luminosity is not only in soft X-rays. So this is not compatible with only a change in absorption. So this is a very interesting change in look AGN. So as an outlook, our method allows to dig into the 20 years of data, and we still have a lot of work to do, especially working on the multi-wavelength aspect of it and anticipating the result of the Vera Cherubim Observatory. Thanks a lot for your attention, and if you have any question, I'm open to it.
Thank you for that excellent and illuminating talk, Eran. I really appreciate it, especially because I'm working on a time domain working group right now, and these questions are constantly on our mind. We have a question from Dirk Gruppe, who asks, why don't you cross-correlate this to the ROSAT X-ray survey that has 1,600,000 soft X-ray sources?
Yeah, so that's an excellent question. So this is, in fact, we took, in fact, ROSAT into account at first, but the spatial positioning of ROSAT is how to say, the position errors with ROSAT are quite large, and this leads to a lot of ambiguous associations. And ambiguous associations lead to very complicated conclusions regarding variability. Because if we associate a galactic nucleus with an X-ray binary that is at the edge of the galaxy, we will get a huge variability factor that is in fact only a spurious correlation. So ROSAT was quite difficult to take into account, and we preferred to simply remove it because of those spurious correlations.
Right. We also have a comment from Pragati Pradhan about a similar methodology that they use for the Athena wide field imager. They provided a link in the Slack if you want to visit that.
Yeah.
I have one additional question for you in the last seconds that we have. You showed us that pie chart. Could you tell us how many of those sources here were completely serendipitous, that is, they weren't a part of the observing program?
Yeah, so about half of them were the targets. So for instance, the QPE was the target of this observation, but most of the variable AGNs were in fact in the cluster where this QPE was found, but basically serendipitous sources around it. So it's about half of them that are in fact serendipitous detections.
Great. And we have some more questions in there. We have time for one more. So I'm going to ask about, do you know this is from Rafael Martinez Galarza. Do you know how much area of overlapping between Chandra and XMM?
I don't know the precise number. I know that a lot of sources are common between XMM Newton and Chandra. On the top of my head, I would say about half of the XMM Newton sources have Chandra counterparts, but I don't know the precise overlap fraction. No, sorry.
That's okay. Yeah, it's a question I had too while I was thinking about it. Jonathan, if you can put your question in the Slack, I will also copy it there if you cannot. So I'd like our next speaker, Erwan, to actually share his slides. We switched that order so I can actually get Erwan's slides up myself. So let me get that for y'all. Okay, take it away, Eran.
Hello, everyone. So second slide, please. So I would like to tell you about how to detect a template in the presence of Poisson noise. I will just start with a reminder for what match filter is. And I will discuss another point, which is how much information do we lose if we use the wrong template or PSF. And then we can dive into what is called the Poisson noise match filter, and I will show you its performance. Third slide, please. So just a reminder, it's a well-known problem, and it's a very well-known solution, that the optimal method for detecting a template in the presence of a Gaussian noise, and these have many applications in physics in general. It's called the match filtering, and all it means is that we need to take the measured image M and cross-correlate it with the PSF of the image P. There are many ways to actually derive this and prove this is actually the optimal method and sufficient statistic, etc. And the most easy way to do it, and also the most powerful, is to use the lemma of Neyman-Pearson, which states that the likelihood ratio test is the most powerful method for simple hypothesis testing. And in this case, all we want to do, is to separate between two hypotheses: the null hypothesis, H naught, that there is no source in the image, and the alternative hypothesis, that there is a source in the image at position Q in this case, and there is some IID Gaussian noise denoted by epsilon. So if you actually apply this to these two hypotheses, derive the likelihood and calculate the likelihood ratio test, you get this result. That is the optimal statistic is basically cross-correlating the measured image M with the PSFP. And the nice feature is that if you go to Fourier space, this becomes a cross-correlation becomes multiplication with the complex conjugate, and this is very powerful because we can use the fast Fourier transform, and this also becomes extremely efficient to calculate. Next slide, please. This is of course used extensively in physics, from LIGO sources to sources in astronomical images. And an important question is how much information do we lose if you use the wrong PSF? So for the simple case of a Gaussian PSF, and if you only consider the width, we can derive this analytically, and this is actually a good example to get an idea of what is going on. So in this plot, you can see in the y-axis, the information loss, or the SNR square, normalized to unity. In the x-axis is the PSF we use, the width of the PSF we use in units of the actual PSF. So one give us the best, of course, And a nice feature is that if we use the wrong PSF, we lose information quadratically. In other words, for example, if we have an error of 10% in the width of the PSF, it means that we lose only 5% in information content. And this actually allows us to construct template banks very efficiently in information that in such a way that we won't lose more than X% of information, for example. And next slide, please. Next slide, yes, thank you. So what happens in the case of Poisson noise? In this case, the basic assumptions are not valid anymore, and we need to go back to Weizmann and Pearson. And after a few lines of algebra, it's actually very straightforward to derive. We find out that the optimal way to do it is, again, cross-correlating the measured image, but this time, instead of the PSF, with some function we call the P Poisson, which is a nonlinear function of the PSF P. Depends on the flux of the source F and the background B. And yes? 1 minute. Thank you. And just to show you an example, on the left side, in the images on the left side, you can see the completeness as a function of flux. The solid line is for the Poisson match filter. Also the PSF and the Mexicanette filtering is shown. And as expected, the performance of the Poisson match filter are basically better than anything else. And in some cases, it actually gives us a factor of a few improvement in sensitivity for source detection. Last slide, please. And to summarize, I just show you that there is a analog for match filtering in the case of a Poisson noise, and we call it the Poisson noise match filter. You can read about it in a paper we published a few years ago. There are many usages except X-ray images, counting cells and many others. And we are currently using this method to reanalyze the entire Chandra archive, and you heard about this yesterday in my talk. Thank you very much.
Thank you very much, Eran. We don't have any time for questions, but the reference to the paper is up here. It sounds like a very interesting read. I recommend you all view that. If we can have the next speaker share their slides, and if you have any questions for Eran, put them in the, actually I'll copy these questions from the Q&A, or you can answer them, Eran, after when the next speaker has started as well. Okay, our next speaker.
Yeah, so hi everyone, and here I'm going to talk about this project. It's about change point detection and image segmentation for time series of astrophysical images. So yeah, so first I'd like to talk about the problem and also the data we are going to use. So the motivation is pretty simple. We want to find something meaningful in some time varying phenomena. So the goal is that first we want to detect the change points. Here, the change points means the time at which some sudden changes happened during the underlying process. And also, after detecting the change points, we also want to identify the sources and locate their spatial boundaries. So the data we are going to use is in this format. It's like a 4D table. So we have some photon counts with the corresponding two-dimensional coordinates, which tells us the location, also the time index t, and also the energy band. So after that, we can treat this 4D table as a series of multi-band images, or actually a video. So these images, and for all these values in the pixel, they denote the counts of photons. So now the goal is pretty simple. We have a video or a sequence of images. We want to estimate the change points, and between two consecutive change points, we want to partition the images. And also we want to estimate the Poisson rate for different regions. And this kind of question is kind of like a model selection problem in statistics. So here we just use this approach. We define an objective function, which is called the model selection criteria. And by minimizing this objective function, we can get the estimation of change points, the image segmentation result, and also the Poisson rate. So that's the general idea of it. So specifically, to minimize the objective function, we define this kind of algorithm. Okay, here I skipped the way to define the function. And also for the algorithm, it's kind of like an iterative algorithm. So the idea is like that at every time we have given a fixed set of change points, we apply some image segmentation algorithm on each of the time intervals. And then we find the corresponding value for the objective function. Then after that, we modify the set of change points and make some updates. We have a new value for the objective function. So after that, we have a sequence of results when we just choose the one with the best value, the best objective function. Then that's the corresponding estimation we get. So after we locate the change points, and there's also another interesting thing is to locate the pixels or the regions that contribute to the change points. So we have to see that before and after this change point, what things changes. So we define some algorithms to detect these key pixels. And so finally, let's share some real examples. So the first one is about the Proxima Century and look at this light curve. So we have 3 energy bands. So we have 3 curves here. The vertical black lines denotes the detected change points. So we can define, and notice that the y-axis are in the logarithm level. So here we plot some information in one time interval. So we have the real images. We also have the fitted image, which can be seen as a piecewise constant function or a segmented image. So, and we also detect the regions such that the highlighted key pixels. So we can see that before this time interval, the intensity increased a lot. And this algorithm successfully detects that region that it increased a lot. And also after this time interval, the intensity in the source decreases. So, and the algorithm also detects this region such that there's an obvious change in the intensity. So the second example is the SDO AI dataset. And so this one is the real images in 3 energy bands. So we can see that there is an object. So as time changes, the intensity of the object changes a lot. And this one is the detected, the fitted image segmentation in different time intervals. So we can see that it detects the boundary of this source, and also it estimates the Poisson intensity. So this one is the last result. So we have the fitted images before and after a change point. And this algorithm successfully detects the region such that there is a significant change in terms of the intensity. So we can see that before the change point, the intensity is pretty low, and after that it increased a lot. So we detect this region of increased intensity. So similarly, we can see there is an obvious decrease in the intensity. So yeah, that's the idea of this method. And so the last part is the light curve. So we also plot the light curve for the source and the background. So we can see that the algorithm successfully separate these 2 parts. So in the source, there is an obvious change in the light curve, while in the background, it kind of keeps stable. So that's all I want to say for this project, and thanks for your attention. Any questions?
Thank you very much for that presentation. Very interesting work. I'd like to point out there's 2 questions for you in the Q&A. We don't have time to address them live, but you're welcome, Cong, to go in there and respond to those questions yourself right now. So if our next speaker could share their slides. Our next speaker is an invited speaker, Michelle Namunka, and she is going to talk to us about the importance of being interpretable towards an understandable machine learning encoder for galaxy cluster cosmology.
Thanks very much. I appreciate it. So I want to lead with what I think would be a very bold claim in any conference other than this one. And that is that astronomy is the ideal sandbox for machine learning. I understand this is probably not the crew that I need to convince. But why? First, there we go. First of all, minimal privacy concerns. We are not dealing with things like patient data where HIPAA violations might be something we need to worry about. When it comes to photons, we are really not concerned about privacy. Astronomy has a culture of shared data. We have well-posed questions. We enjoy public interest and support really across the political aisle. And our data are non-monetizable. Some might say worthless. I like non-monetizable a little bit better here, but they really can't be used to sell anything. Of course, that doesn't exempt us from ethical concerns, but we really do enjoy a lot of freedom for these reasons when it comes to applying machine learning to our questions. But this group, I think, needs to wrestle with a slightly different question. Astronomy is well suited for machine learning, but is machine learning the right tool for astronomy? And here, I think there are two main areas that we need to explore. The first is, can machine learning be trusted? Can we establish proper standards for interpretability and for understanding our failure modes? And the second is, can machine learning be used to make new physical discoveries? Can it point us to things we might not have investigated on our own? And these two questions, the question of machine learning trust and the question of new physical discoveries, is what we're going to be exploring today. So for this work, I'm exploring galaxy clusters as a cosmological probe and applying machine learning to that question. So let's build up a little bit of background on galaxy clusters. So the obligatory sentence here is, galaxy clusters are the most massive gravitationally bound objects in the universe. They contain hundreds or maybe even thousands of galaxies, all gravitationally bound. And here you are seeing a composite image of Virgo. You are seeing the galaxies in optical, and you are also seeing in X-ray the hot intercluster medium. That is the purple haze kind of around it. And that's the bit that we'll be focusing on today for obvious reasons. So clusters, they're massive. They inhabit the high mass tail of the halo mass function. And when it comes to cosmology, if we can count them up as a function of their mass and as a function of their redshift, we can use that to constrain cosmological models. So here's what I mean by that. Here I'm showing on the x-axis cluster mass, on the y-axis abundance, and a number of different sigma 8 cosmologies, from the low sigma 8 in the yellow solid to a high in the blue dash dotted. All right, so you can now imagine that if I can measure my cluster masses and bin them up, I can compare them to these models and I can use that to constrain sigma 8. So big idea here, cluster abundance is sensitive to the underlying cosmology, especially sigma 8. Same figure, but with a different title. And this title says mass bias versus cosmology. So for this, I want to now talk about what it means to measure masses and how a bias in those masses might affect our results. So I want you to just mentally take that green dashed line, and I want you to bias the masses by sort of sliding it to the right or sliding it to the left. And you can see that mass bias and cosmology are really degenerate. It can be hard to disentangle a different sigma 8 from biased masses. When it comes to X-ray observations, we will often use weak lensing masses to help with that calibration. For this work, I am using simulated galaxy clusters. These are from the Magneticum Cosmological Hydrodynamical Simulation, which was run at the WMAP7 Cosmology. That's a low sigma 8 cosmology. It has a box size that is large enough that I get a really diverse population of clusters, but it is high enough resolution that I can see what's going on in the cluster cores and get realistic descriptions of cluster outskirts. And making a Chandra-like mock observation of these, you can see a sample of them below. I will comment here that in a few moments, rather than working in the two-dimensional image space, like the ones I'm showing here, I'm going to describe these clusters as profiles. So I'll summarize them a little bit more compactly than the information you're seeing here. Okay. This is the last slide with this particular plot. But the last thing I want to bring up today is that for this work, I'm going to need to build many cosmologies from one simulation. And so the way I'll do that is by changing the selection function. So the one you saw earlier and the one you're looking at right now is a volume limited sample, meaning these models show every cluster in a given volume. In fact, X-ray surveys will typically have not only a volume limited sample, but also a flux limited sample, meaning at the low mass end, we're really going to only pick up on the very bright objects. Okay, so I've built kind of a toy model here where you see for a number of different cosmologies, my stitched together flux and volume limited samples. There actually is some uncertainty in where that stitching might take place due to the mass bias issues that we talked about earlier. All right, so this next figure is intentionally messy, where I'm showing you here just the range of possibilities for such selection functions. In the color, you're seeing the gradient of cosmologies, the gradient of sigma 8. Don't read too much into the discretized stitch points here. That is just an artifact of my binning. If I had binned more finely, that would be more continuous. All right. So from this, the takeaway is that typical X-ray surveys include both a flux and a volume limited regime. And there's also uncertainty in the mass at which these two join. So there are a variety of different cluster abundances that might be expected. In a moment, I am going to introduce a machine learning technique that learns from two-dimensional arrays of data. And here I'm showing a couple of visualizations of how I'm going to organize that data. So just working from small to large, in a pixel, I am going to put a cluster observable. So that might be something like a cluster temperature or the cluster core gas mass. In a row, I am going to order all of that information about a single cluster. And my image is going to be made up of a simulated cluster sample for one of those selection functions that you saw earlier that varies with sigma 8 and varies with the stitch point for the volume and flux limited samples. Okay, this piece is important, so I want to repeat it one more time. A row contains a single cluster. Here I'm showing different groups. So I have them numbered here quite tiny, but they go with this key here. So that first pixel is temperature. The next 7 are a gas mass profile derived from the mock observations. And the last 7 are a gas density slope profile, also derived from the mock observations. So the big idea here, we have simulated realistic cluster samples from many cosmologies and have cast each into a two-dimensional array. Let's talk about the machine learning tools, neural networks and encoders. So we will just build up in complexity over the next couple of slides, starting with a neural network. So a neural network is a class of machine learning algorithms that takes some input, I'm showing here in white, processes it through a number of unseen layers, I'm showing here in green, to give some final output, which I'm showing here in the dark purple. So in my case, I've got 9 inputs, I've got 1 output, and I've built this architecture with 3 hidden layers. The way these layers work is a neuron is some linear combination of all the neurons in the previous layer, plus some nonlinearity added on for good measure. Likewise, this one is a linear combination of the previous, and this one is a linear combination of the previous. We could go the whole way down. Going to the second hidden layer, linear combination, all right? By building up these linear combinations, plus the nonlinearity that happens at each neuron, I can approximate any function. And in this case, I've got a function with 9 inputs and 1 output. Moving up a layer in complexity, this is an autoencoder. So an autoencoder takes an input signal and tries to reproduce that same input signal by processing it through these hidden or latent layers. And it pushes it down to a bottleneck, which is the one that you see in dark purple. It trains the same way as the neural network I showed before, but you can think of this one as a flexible version of principal component analysis. Here, I've asked it to take some signal and summarize that signal with just a single parameter. You could use more than one parameter depending on your use case. Okay. As you can guess by all of these lines and connections, this is going to get very busy very fast. So I'm going to abstract away all of those hidden layers, and I'm just going to represent them as blocks. So here is my autoencoder again with some input signal, some output signal that is hopefully the same, an encoder and a decoder, and in the middle, some terse representation of the signal. Okay. We're now ready for the architecture that I'm going to be using for this work. It looks like this. So what I've got here is an encoder that takes my clusters, remember they live in a row. It takes a single cluster and it boils it down to its most essential piece. It boils it down to some terse representation. I then have a network that takes that list of cluster values and estimates some output, some cosmology at the end. So this follows what an astronomer would do. This is exactly the way we would do it using traditional methods. If you handed me cluster observations, what I would do is I would take those temperatures and gas masses, and I would boil them down to cluster mass. I'd come up with some mass proxy. I'd then take a list of cluster masses, and I would compare that to the models, and I would estimate a sigma 8. So it just follows sort of the way our brains work. There's a really good physically motivated reason behind why we would do it this way. And that is that by building the model this way, we're getting the maximum information per object as a first step, which is typically a better approach that will yield more robust results than something like stacking, especially if you've got good observations, if you've got a really diverse sample. Right. The other reason why this is a really nice architecture to use, in addition to the fact that it follows the way a human would do it, it also has this checkpoint at the middle. So I said to you, I do it the same way. I would build a mass proxy. And so we have this midpoint checkpoint, this kind of mass proxy that we can explore. So big idea here, this encoder is engineered to mimic a human approach to the task. It takes cluster observables and turns them into a mass proxy. It takes that list of masses, those mass estimates, and it estimates a cosmology. How does it do? Here what I'm showing is true and predicted sigma 8 with a 1-to-1 line. And you can see that it performs much better toward the middle. At the edges, it tends to bias toward the mean a little bit. It underestimates up here, overestimates down here. This is a really common failure mode of machine learning. ML interpolates a lot better than it extrapolates. And so it tends to bias toward the mean on edge cases. But toward the middle, this is estimating sigma 8 at about the expected theoretical limit. So got a scatter of about 0.02, which is what we would expect for a cluster sample of our size. Okay, I'm about halfway through my talk and I have presented results. And the reason we're at results here is because we are just getting started. We are not done with this machine learning algorithm yet. I told you that it performs at about the expected theoretical limit, but this is not where we claim victory, because the next thing we have to do is interpretation and go back to those big questions at the beginning, ask how this is working and if it can point us to something new. So the questions: can machine learning be trusted? And can it drive physical understanding? To answer the first question, we're going to look at terse value correlations to assess whether the model will generalize. These can help us to trust our machine learning models. The second thing we'll do is we'll look at saliency maps to identify what part of the cluster carries the most cosmological information. And these can lead to machine learning driven discoveries. So the first one, correlations leading to trust. All right, the big idea here is we want to visualize how the terse layer correlates with cluster parameters. Remember, this terse layer is our checkpoint. This is something like a mass proxy. And we're going to go in and we're going to take a look at it and visualize how it correlates with cluster parameters and just see if it makes sense. This will help us to build trust in the model by asking, is the terse layer summarizing sensible features? We're going to look side by side the trustworthy results that I present through the rest of the body of this talk and some suspicious results that you'll see on the right-hand side here. Okay, the trustworthy results I said were at about the expected theoretical limit, and the suspicious results are a factor of 10 better than theory says I should be able to do with a cluster sample of my size. Is this trustworthy? And will the model generalize to real data? Let's look. Okay, here what I'm showing. In the x-axis is my terse layer value, and on the y-axis is my mass. Remember I said that I expect my terse layer to be sort of a mass proxy. And in the trustworthy results, indeed, that is the case. My machine learning algorithm has come up with a mass proxy. The units are not physically meaningful to me, but it is indeed a mass proxy that correlates very tightly with mass. It figured out how to find mass from those observables. My suspicious results are completely uncorrelated with mass, and that makes me nervous. I want to know, why is the terse value uncorrelated with mass? This is a giant red flag that something isn't right. So let's dig a little deeper. Here I'm showing correlation of the terse layer value with the underlying cosmology, the sigma 8 value. Okay, my trustworthy results do exactly what I think they should do. A single cluster, not the way that I have observed them certainly, should not encode the underlying cosmology. You need a sample of them for that. In the left, you see my terse layer value is completely uncorrelated with sigma 8, and that is exactly what I expect. On the right, the suspicious results, the terse layer value is tightly correlated with sigma 8, and now I have found the problem. What has happened? The model picked up on a cosmology-dependent simulation artifact. So it picked up on something that is just particular to the sims. It latched onto that, and it said, I can figure out sigma 8 just from a single cluster. So the verdict here for the suspicious results, machine learning cheated. I was only able to figure it out by building this architecture that followed the way a human brain would do it and build these checkpoints in the middle. These suspicious results, they are not robust. The model will not generalize to real observations because it depends on a simulation artifact. All right, so we just talked about terse value correlations. The big idea in this subsection was we were visualizing how the terse layer correlates with cluster parameters to build trust in the model by asking, is the terse layer summarizing some sensible features? And by doing that, we were able to identify a case where the results looked phenomenal, but it turns out that ML was picking up on a SIM artifact. All right, now let's talk about saliency leading to discovery. So the big idea here is we are going to assess the importance of each cluster feature by looking at gradients in the encoder network. And we will ask, how does changing the input change the terse value? All right, we are going to look at d terse by d input. This will help us to develop a physical framework for understanding surprising results. We're going to start with this picture of a horse. Unfortunately, I cannot see the Slack or the chat. If I could, I would ask you the question, how can you tell that this is a horse? And how can machine learning tell that this is a horse? You should please feel free to discuss amongst yourselves how you can tell that this is a horse and how machine learning can tell that this is a horse, but I cannot see your answers. So I'm going to have to make some guesses as to what you might say. So you might know that this is a horse because it has 4 legs. You might know that it has a mane, much like a horse. You might recognize the particular face and nose shape that looks like a horse. All right. There might be someone probably sitting in the back if this was a real conference, who might raise their hand and suggest that they can tell that it's a horse because it is on a green pasture with a white picket fence behind it. And I would welcome that response as well, because maybe machine learning is picking up on the things we expect it to, or maybe it's picking up on things that are not exactly in our mental definition of a horse.
3 minutes.
Thanks. So there was a really interesting paper that explored this with saliency maps. And they found that the most important thing for identifying a horse was the existence of a copyright stamp in the bottom left-hand corner of all of the horse pictures in their training sample. Here's a figure from that paper. They looked at these saliency maps. They looked at heat maps of pixel importance. And in this top left hand, they had a picture of a horse with the copyright stamp. And that copyright stamp was super important. This image is classified as a horse. Remove the stamp, it is no longer classified as a horse. Even more concerning, add the stamp to a picture of a convertible, and it is classified as being a horse. If astronomy is going to trust our data to machine learning, we need to understand these failure modes. So I have looked at saliency maps, looking again at how the terse value changes with input. And the nice thing about my ordered data is that you don't have to make any sense out of this figure on the right-hand side. I'm going to summarize it for you. So here I have, as a function of mass, what is the saliency? How much attention is the machine learning algorithm paying to this particular mass range? For the standard catalog in teal, it's pretty flat across the entire mass range. For a catalog where we have removed weak lensing, remember weak lensing is that hook for calibrating masses, for removing the bias in masses. In the place where we've removed that information, ML gets really interested in this middle mass range, which not coincidentally corresponds with the transition range where the volume and flux limited samples stitch together. So we can now ask, is the model finding that transition point between the flux and volume limited samples to calibrate the masses without weak lensing? And the answer is a resounding yes. Here I'm showing on the x-axis number of clusters, on the y-axis an observable proxy for that stitch point. The colors are the average sigma 8. So if you took this to Vegas and I told you there were 110 clusters, with a median YX of 14.15, you would look at the average here, you'd pop up here, you'd say, I'm going to guess a sigma 8 of about 0.83 plus or minus 0.03. This is exciting. This is a new self-calibration mode that was enabled by machine learning. So it pointed us to this idea that the median and the integral under that selection function is correlated with cosmology in a way that we can exploit. This will be really important for all-sky surveys like eROSITA, which will typically rely on weak lensing mass calibration to be able to calibrate the masses underneath. This is one that can be done entirely with X-ray observations. So we just finished talking about saliency maps, assessing the importance of each feature by looking at gradients in the encoder network to develop a physical framework. And now let's go back to our question at the beginning. Is ML the right tool for astronomy? I think that it can be if we engineer models that follow a human approach with checkpoints to make sure that the model is learning something sensible. If we interrogate and interpret our models. If we approach high accuracy results with scrutiny. And if we treat machine learning as a tool to be used in partnership with traditional statistical methods and human exploration. I'll put a summary of the key questions and the ways we addressed them here. Please keep an eye out for Namaka and Vaklinen. It is currently under review, but should be coming soon to an archive near you. Thanks very much.
Thank you, Michelle, for that excellent talk. Lots to think about. I think you gave us some big things to think about, in fact, and ways to look at our science and our field in a different light. That's very awesome. If we have any questions for Michelle, please add them to the Slack or to the Q&A. I do see several people typing now, so I'm not gonna steal too much time with my own question, except to say that I really appreciated how you likened this to a machine learning version of PCA. I think when we saw that layer there in the center, it really put that into perspective, and a nice correlation with the mass also. It's not really a question. Sorry.
Yeah, that's all right. I'll comment on your earlier comment, which is it's a shame that this is a virtual conference, because I would love to sit down over coffee with folks here and be able to talk about some of these things that we as data scientists should be wrestling with as we try to pull our field in a direction of trusting machine learning and data science. I think these are some of the things we need to communicate with astronomers as we're developing new methods. Yeah.
I agree. Okay, we have a question from John Zuhone. For each cluster, you provided the algorithm T gas mass profile and gas density slope profile, if they heard you correctly. But aren't the last two related by taking a couple of derivatives so they provide the same information?
They are. John, machine learning can require a little bit of hand-holding to extract information from these data points. And you are absolutely right. Those mass density profiles, we expected to pick up on something like the mass accretion history in the core. In fact, we did not, which was a surprising result. And we believe that as we can build cluster samples that are built from large suites of SIMs where there are a variety of different merger scenarios, that might become more and more important. But you're right, it turned out that those density profiles were not some of the most informative pieces of information in the input.
I wonder if that could be used to find hidden correlations between different variables if you see a similar type of non-information content.
Yeah, I mean, I believe there's really a lot to mine from an approach like this, where you can kind of pop the hood in the middle and look at correlations. And so, I would love to see this kind of two-stage architecture be adopted for other science questions outside of the ones that I'm exploring, because I think there's just a lot of opportunities there to learn new things about what's important.
Awesome. Thank you so much again. That's all the time we have for this talk. If you have any more questions for Michelle, please do put them in the Slack. I think Michelle is happy to address any additional questions there. If the next speaker could be prepared to share their slides. Our next speaker is Mauricio Elias Chavez from the Instituto Nacional de Astrofísica, Óptica y Electrónica. Is going to talk to us about X-ray sources in the 1.5 megasecond ultra narrow deep field observed by XMM Newton. Take it away. I do not hear you if you are speaking.
Okay, sorry. So, hi everyone, and thank you to the organizers for giving me the opportunity to present this talk. I am Mauricio Le Chavez. I am a PhD student at the National Institute of Astrophysics, Optics, and Electronics in Mexico. And today I'm going to tell you about the results in one of the deepest X-ray surveys performed by XMM Newton. The survey is made by 13 observations taken over 2 years from 2015 to 2017, with a total exposure time of 175 million seconds. In a field of 30 times 30 arc minutes around the bright blazar 1ES 1553. Additionally, in this field, we have infrared-wise public data and an optical follow-up with the 10 meters GTC telescope. Now, I am going to present some of our results. First, we found 301 point light sources with a 3 sigma of significance. In the right plot, I showed you our flux distribution. Here we reach a flux limits of 10 to minus 16 ergs per second per centimeter squared in the soft and full band, and 10 to minus 15 in the hard band. As a comparison for our results, here I show you some of previous XMM, Chandra, and other surveys. Here we can see how our results are marked with the black star and light just above some of the deepest surveys performed by XMM Newton with the green dots. The blue dots is for Chandra and the others with the red. Then we cross-correlate our X-ray sources with an optical catalog from our own GTC observations and WISE public repositories. As a result, in the upper panel, we found 244 optical and infrared counterparts, which represent 81% of our catalog. In the next step, we compute the photometric redshift of our sources with the program Photoraptor. In the lower panel, we show the redshift distribution with photometric and spectroscopic redshift up to 2.7, with 15% of all sources present spectroscopic measurements. Then we compute the hardness ratio distribution of all sources. The hardness ratio is defined as the ratio between the soft and the hard core rate bands, and it can give us a good approximation to distinguish between obscure and obscure sources. I mean, sources with column density higher than 10 to 21. Here we found that 30% of our catalog of obscure and 88% of them present a column density higher than 10 to 22. Finally, we use 3 criteria to identify AGNs. The first is a typical AGN X-ray luminosity threshold of 10 times 10 to 42 ergs per second. The second and the third criteria are based in the X-ray to optical and infrared flux ratio. In the upper panel, we can see the X-ray fluxes versus the Erwan magnitude distribution of our catalog. The gray area in the plots is used as the selection region of AGNs. As a result, we found a total of 204 AGNs, of which 41 are classified as quasars and 139 as Seyfert galaxies, based in their X-ray luminosities as we present in the lower panel. I have to mention that this work and all of our results are presented in Elia Chavez et al. 2021. So I leave my conclusion here and thank you for your attention.
Thank you very much, Mauricio, for that very interesting talk. Do we have any questions? We may have time for a quick one. We have about 30 seconds. If we have no questions, I do encourage you to ask if you think of one later in the Slack channel, and Mauricio can join and address it there.
Okay, thanks.
Thank you very much. Our next speaker, if you can start sharing your slides, is Venki Ramkrishnan, and is going to speak to us about, is coming to us from the University of Concepcion, and is going to speak to us about multivariate modeling framework for non-uniform sampled light curves.
Yeah. Thank you. Thanks for the organizing this meeting. I'm going to be talking about something that hasn't been given much importance to when it comes to modeling the light curves or interpolating the light curves as such. And having already heard a lot of talks on time series, I'd like to just give a short preview, however, on the existing light curves that we have on hand, which is mostly using long monitoring campaigns from the likes of Rossi X-ray Timing Explorer, NICER, or SWIFT, and for dedicated pointed observations, we also have Chandra and XMM Newton. Well, when it comes to time series, of course, it's mostly the active galaxies or X-ray binaries and pulsars that gets their precedence. And of course, in the modern era, it's mostly the multi-messenger astronomy that has been given more importance to unravel further information on the physics of the underlying emission mechanisms. One thing we know that coordinating any multi-frequency monitoring campaign is quite a complicated effort. It needs quite a lot of planning, and having more than one or few campaigns is going to be very challenging. And I'm sure efforts are already in play in order to close this gap. But what this also means is that there's inherent sparsity in the with regards to the cadence, and hence also the non-uniformity and the sampling of the data, which is actually is more important, as given that the importance is more towards getting milliarc-second scale precisions when it comes to estimating periodicity or some any other variability timescales. So we know some of the tricks that we use in literature are mostly banking on linear spline interpolations. And of course, they are also tested as robustly as possible using Monte Carlo simulations. But on the other hand, we got the forward modeling tricks, which uses a covariance matrix like the damped random walk modeling methods. But using covariance matrix already, there is an implicit assumption of the stationarity because of the heavy use of diagonal matrix, diagonal components of the matrix. And also, most of these techniques also works on a single frequency or an energy band at a given time. Hence, with all this given assumptions, we developed an algorithm that uses what we call as a local linear regression that also makes use of the intersection confidence intervals, wherein we take the multivariate data from multiple energies, multi-frequencies, and interpolate the light curves or time series in such a way that the stationarity or non-stationarity is not lost. And the main reason we do that is basically, the way we do that is by having an adaptive windowing function, perhaps a Gaussian or a rectangular function in the time domain. And from the frequency domain, we use a wavelet or a polynomial filters to do the interpolation. As far as the intersection confidence intervals method go, this is a quite robust technique where you can get an adaptive estimate of the scale that is required in order for the windowing function. So yeah, as I mentioned, this is a trick that works, that has been developed for multi-band light curves. And just to show an example here, is a light curve that we use at the B and B band. And the trick here is to work directly on it's a joint interpolation technique, hence working directly on multiple bands here. And you can also, of course, synthesize light curves at an intermediate frequency or an extrapolate to another bands outside this interval, hence also giving more robustness to the analysis and that we carry on with these light curves.
1 minute.
The important thing to remember here is the variance that we take into account, Gaussian elements or the Poisson noise levels that we have from X-rays, and the point spread functions from the telescope, the response matrix. Hence, you can also robustly take the noise correlation into account when mixing up multiple telescopes. So I just leave here with the prospects, and also to say that these techniques can also be extended to image domain methods as robustly as possible. And of course, in the future case, polarization of X-ray data, where the Rice noise distribution also gets aliased with the Poisson noise and has to be given more significance in the near future. Thank you so much.
Thank you, Venki. Sorry for clearing my throat. I thought I was muted. It was unrelated to you. We don't have time for questions for Venki here, but I found that very interesting. I actually forgot to give you the 2-minute warning because of that. But if you have any questions, put them in the Slack channel, and hopefully Venki can join us there for discussion. I'll ask our next speaker to share their slides. Our next speaker is Lorena Hernandez Garcia, coming to us from the Millennium Institute of Astrophysics, and is going to talk to us about the ALECER broker. You're muted right now, Lorena.
Sorry. Good afternoon. I'm Lorena Hernandez Garcia, and I'm going to present you the ALECER broker, which is based in Chile, and it might be helpful for those who are doing multi-wavelength analysis. So ALECER means automatic learning for the rapid classification of events. As I said, this is a broker, which means that it is an intermediary between large attended telescopes and the scientific community. And since 2019, ALECER is ingesting and processing the public alert stream from the Week Transient Facility, or CTF, which generates about 1 million alerts per night. And this is in preparation for the LSST or Vera Rubin, which will start working very soon and will generate about 10 million alerts per night. So this is where the brokers come. And in fact, ALECER is one of the 7 official brokers of the LSST and comes to help the scientific community. In particular, ALECER is a team composed by astronomers, engineers, computer scientists, and mathematicians. So let me explain you how the pipeline works. So when there is a variable event in the sky, then this generates an alert which goes to the CTF stream, and then this triggers different processes, which takes about 1 second to compute. And among them, there is a crossmatch to have some contextual information. And then we use a stamp classifier to classify to a close classifier of the source. And when we have more detections, then we can make the light curve, process it, compute the features, and classify the sources and obtain outliers. So with all this information, this goes to the alerts stream, and then we have provided classifications for the scientific community to work with the data. So the ALECER is pioneer in classifying sources using machine learning. We can classify sources up to 15 astronomical classes. You can see it in this tree here. And so the classifiers are 2. One is based on images, is the stamp classifier, and another one is the light curve based classifier, which uses the light curves. And here you can see the confusion matrices of both of them. ALECER also has different products that are available and public for the community. So let me show you very briefly. So we have the Explorer, which is useful to search and visualize your favorite source using the coordinates or the name. We also have Jupyter notebooks focused on different science cases. And we are also working on watchlist, which allows you to make crossmatch in real time. We have also the Supernova Hunter, which is a web interface that allows you to search for very young supernovae. And we also work with data releases that allows to have a more complete light curve. And here there are some key numbers. I want to focus on the 178 features that we compute per object. And this is a public library that can be downloaded and used and allows you to make some cool things, as for example, this is an example of an AGN where we have light curves in the radio, optical, and X-rays. And we can use this library to compute the variability features for all these light curves, independent of if they are from CTF in the optical or other. So also notice here that when you use optical data to complement X-ray data, for example, you can have something like this where the variations are more better observed because the sampling is better. So finally, I want to leave you with these links to Alerce. So please, if you find it useful, go and test it and let us know if we can do something for you, because we are working with and for the community. Thank you so much.
Thank you very much for that interesting presentation. Very cool stuff. We have about 30 seconds for questions. If we have any, please put them in the Q&A or in the Slack channel. I have a question. You said that I have two questions. You said this is one of 7. How is it going to be? Is there going to be a process to make a primary alert service, or is it going to be always going to be duplicated for benefit?
No, the idea is that there are 7 brokers that have been selected like about 2 weeks or 3 weeks ago, and they are all over the world, and each of the broker can do whatever they want, but the alert stream will be the same.
Okay.
But this will be distributed. You cannot access to the data, to the alert stream yourself. You have to access it through a broker. And the other for the Vera Rubin, not for the CTF. For CTF, anyone can access.
Right. And you did mention, you said there was a 1 second required spec on that on ZTF, where there's that 1 second time that it takes to get through. Is that the most optimized, or or faster, even faster triggers or faster notifications in the works?
This is to obtain the data from the CTF stream. Then it takes some more seconds to do the stamp classifier and the light curve classifier. But this is to ingest the data from the CTF stream to the Alerce pipeline.
Okay. Thank you again. If you have any questions for Lorena, do add them to the Slack discussion. If you have any questions about this broker, also definitely ask them in the Slack discussion. Thank you all. This wraps up our first session for today. We have another session coming in about 30 minutes. So we're going to close this session now. We'll open up using the same Zoom link for that session. Thanks again for joining us. I hope to see you at 2 o'clock Eastern time.